We're going to talk in this lesson about a few more definitions for vectors, and we're going to break them up in components and perform some vector operations. So the first thing we're going to talk about is the magnitude of a vector, and that's the length. So the magnitude or the length of a vector, when I have its component form, well, let's take a look. If I have v1 and v2, the magnitude is going to be represented by, and it's the absolute value symbol, but we don't just take the absolute value of this. The magnitude is going to be what you get when you do the Pythagorean theorem. So the magnitude of a vector is going to be the square root of the x component and the y component. And it's just like the radius when you're trying to find polar form, the radius of polar form, or the radius when you have an x and a y value in the Cartesian plane. So we're going to find the magnitude of a vector, and our first example is going to be vector u is equal to 2, negative 3. The magnitude is just, and again it's represented with absolute value symbols, but that doesn't mean you just take the absolute values. The magnitude is a single number when you get done. It's a scalar, and it's 2 squared plus negative 3 squared. Please remember, anytime you square a negative, you get a positive. So that's the square root of 4 plus 9, which means the magnitude of that vector is going to be radical 13. So that's magnitude. We're going to talk about something called a unit vector next. So if I looked at this vector, we'll call him vector w. And w's components are 3/5 and 4/5. Let's find the magnitude of w. So the magnitude of w is the square root. If I square 3 over 5, I get 9 over 25. And squaring the other one, I get 16 over 25, which when I add those two together, I get the square root of 25 over 25. And that simplifies down to 1. So when a vector's components, when the magnitude is 1, we call that a unit vector. So a unit vector is any vector that has a magnitude of 1, in which what this vector w would be. Okay, so the x and y components, when you do the Pythagorean theorem, you end up with a value of 1. Now we have two common unit vectors that we use quite a bit. And the first one is when the vector is pointing completely in the x direction, and this is vector I. Now, vector I, in a textbook, he would be bolded. Since he's not bolded, I put my little hat on him. You don't confuse him with the imaginary number I. This is completely different. Vector I has components of 1 and 0. So he points entirely in the x direction with a unit of 1. Vector j, so here's the other special vector. Vector j points completely in the y direction, so his components are 0, 1. And a lot of times we use these two vectors. Instead of using the brackets, we actually attach a magnitude next to these vectors to indicate the x direction and the y direction. They're now the I and j directions. So that's what we want to do. We want to represent a vector in terms of I and j. So here's what that looks like. The vector, if I have v1, v2, can be expressed in terms of I and j like this. Our vector v is equal to v1i plus v2j. So instead of using the brackets, we use an I and j. So here's an example. We have a vector u, and we're going to say u is 5, negative 8. All I want to do is express vector u in terms of I and j. It's pretty easy. All you do is you get rid of the brackets, and you say 5i minus 8j. Or you could say plus negative 8j. Either way. You wouldn't see plus negative 8j in a textbook, so that's why I wrote it like that. So we can add vectors with I in terms of I and j, just like we added components yesterday without I and j. If I have vector u is 3i plus 2j and v is negative I plus 6j, I just want to find u plus v. Basically, you add the i's together and you add the j's together. That's all you do. So u plus v is going to be 3 plus negative 1, so that's 2I, and 2 and 6 is 8j. 2I plus 8j. So we can also start with a vector given its magnitude and direction. So this represents the magnitude, this next represents the direction, and find the vertical and horizontal components using some right triangle trig. So if I'm given theta and the magnitude of a vector, and think of our right triangle here, we want to find something to represent v1 and v2. Okay, so I know the cosine of theta in this diagram is going to be v1 over the magnitude of v. And the sine of theta is going to be v2 over the magnitude of v. So, if you cross multiply, you can end up with a representation for v1 and v2. So let v be a vector with the magnitude of v and a direction theta. Then, in component form, my v1 component is going to be the magnitude times the cosine of theta, and v2 is going to be the magnitude times the sine of theta. I can represent this as a single vector in terms of I and j by writing this. Vector v is now going to be equal to the magnitude of v times the cosine of theta, and that is all in the I direction. That represents v1, and the magnitude of v times the sine of theta, and that's all in the j direction. That represents v2. So that's how you can write it in component form in terms of I and j. So here's an example. If vector v has a length 8 and a direction of pi over 3, we want to find the horizontal and vertical components and write them in terms of I and j. So, based on our formula, we know that v1 is going to be the magnitude times the cosine of theta, and v2 is going to be the magnitude times the sine of theta. So v1 is going to be 8 cosine of pi over 3, and v2 is going to be 8 times the sine of pi over 3. I can go ahead and evaluate this. Pi over 3 is an exact, is an angle that is a special angle, so the cosine of pi over 3 is 1/2, which means v1 is going to be 4, and that's going to make v2 4 radical 3. So in terms of I and j, you say my vector v is 4I plus 4 radical 3j. There really isn't anything complicated here. You just have to remember your trig, which is why trig shows up again and again and again. Remember your x component is the cosine, the y component is the sine. Remember your special angles and your exact values, and then put them in terms of I and j. So now let's say we have the components v1 and v2. We've already talked about how to find the magnitude, which is using Pythagorean theorem, but if we want to find the direction, we need to use the inverse tangent, because we know the tangent of theta is going to be v2 over v1. So the direction is going to be the inverse tangent. But just like we talked about with polar coordinates, we have to be careful with our direction, because your calculator will only give you first and fourth quadrant answers. It's always good to sketch it to make sure that you're in the correct quadrants. We got to watch the quadrant with these. So we'll finish with this example. Find the direction of vector u, where he is in component form negative radical 3I plus j. So if we want to sketch this, negative radical 3 1 is going to be in the second quadrant. So that's where we have to be careful. This is negative radical 3, and this side is 1, and we're trying to find theta. So what your calculator is going to give you is the fourth quadrant angle, I am guessing. So theta is going to be the inverse tangent of -1 over radical 3. And if you put that in your calculator, you are going to get -30 degrees out. But that's not where we are. We are not down here. We are up in the second quadrant. So you have to add 180 to that. And my direction is now 150 degrees. If I wanted that in radians, that would be 5 pi over 6. So component form, I and j, to denote x and y direction, and magnitude is Pythagorean theorem, and then finally direction itself is the inverse tangent, and we always have to watch our quadrant angles. So we will practice more of this in class.